Last episode, you assembled Adam piece by piece, momentum to remember the direction, RMSProp to size each step, and the bias fix so the first few updates don't undershoot. We ended on the claim that Adam just works. Tonight, you test that claim. Same starting point, same hill, same 200 steps. 4 optimizers race. Plain SGD with momentum, RMSProp and Adam. 1 chart, 4 curves, 4 final losses. By the end, you'll see exactly how much the update rule buys you. And the gap is bigger than you'd guess. Here's the track. It's a Rosenbrock style valley, a long, gently curving banana of a canyon with the floor at the bottom. Every runner starts at the same red dot up on the wall. The misconception to kill right now. They all walk downhill, so they all end up in the same place. They don't. Downhill is not one direction, it's a different direction at every point, and the floor of this valley curves. How you decide your next step, given the slope under your feet, decides whether you reach the floor in 200 steps or you're still stuck on the wall. Start with the honest baseline, plain SGD. Step in the direction of steepest descent, scaled by the learning rate, full stop. The misconception people carry, steepest descent points at the goal. It doesn't. On a curved valley, the steepest direction points mostly across the canyon, into the opposite wall, not along it toward the floor. So vanilla SGD zigzags, wall to wall, creeping forward a sliver each bounce. After 200 steps, it's the magenta dropout of the 4. It lands at loss 0.42, still up the slope. Not broken, just slow because it forgets everything it learned one step ago. Now bolt on momentum. The misconception, momentum is just a bigger learning rate. No, a bigger learning rate amplifies the zigzag too, and you diverge. Momentum is memory, it averages your recent steps. The side-to-side bounces point in opposite directions, so they cancel. The forward crawl points the same way every step, so it accumulates. The runner stops slamming walls and starts sliding down the canyon's length. Same learning rate as plain SGD, just a velocity that remembers. It finishes at 0.08, more than 5 times closer to the floor. RMSProp attacks a different problem. The two axes have wildly different steepness. Across the canyon it's a cliff, along it a gentle ramp. The misconception, one learning rate should fit the whole landscape. It can't. The rate that's safe on the cliff is glacial on the ramp. RMSProp keeps a running average of each direction's squared gradient and divides by its square root. Steep, noisy directions get a small effective step. Flat, quiet directions get a big one. It auto-shrinks the cliff axis and stretches the ramp axis. Result 0.05, even closer than momentum. Adam is the obvious move. Take momentum's memory of direction and RMSProp's memory of scale and run both at once. The misconception worth naming, combining two good ideas just averages their performance. Sometimes. Here it compounds. Momentum picks the right heading down the canyon. RMSProp sizes the step right for each axis along the way. The bias correction from last episode keeps the opening steps honest. Adam reaches 0.03, the deepest of the 4, the tail curve that dives first and flattens lowest. Look at the 4 numbers together, 0.42, 0.08, 0.05, 0.03. The jump that should stop you is the first one. Plain SGD to anything with memory is more than a 5x improvement. From one idea, don't throw away last step's information. The refinements after that, adaptive scale, then both together, each shave the loss further, but they're smaller gains stacked on that first leap. The misconception this kills, the fancy optimizer is where the magic is. The magic is memory, Adam is memory done thoroughly. One honest caveat so you don't overlearn this. Same hill, same budget, same tuning effort. That's what makes it a fair race. Change the surface or tune SGD's learning rate harder and the gaps shrink. A well-tuned SGD can match Adam on many real problems. What's robust is the ranking under equal effort. The more an optimizer remembers, the less hand tuning it demands to land in the same place. Adam wins the default not every race ever run. That's why it's the button you reach for first, not the only button. Open 10 Optimizer Showdown.py. It's a single bake-off harness. Define the Rosenbrock toy and its gradient. Write 4 update rules as small stateful functions. Run each for 200 steps from the same start. Log the loss every step and print the 4 finals. No training data, no net, just a 2D surface and 4 ways to walk down it. The figure is the 4 locked curves overlaid. The surface first. Rosen returns the scalar loss. Rosengrad returns the 2-vector gradient. Classic Rosenbrock. A x squared plus b y x squared with over 1 b 100. The minimum sits at 1 by 1 where the loss is 0. That b out of 100 is what makes it nasty. The y x squared term is 100 times stiffer than the a x term, so the canyon is steep across and shallow along. This is the same ill conditioning idea as our OPT bowl, just curved instead of elliptical. The shared setup, every optimizer starts at start, OS 1.5 2.0, runs for steps for 200, and we see nothing because there's no randomness. The race is fully deterministic, which is the point. Same start, same hill, only the update rule differs. We keep one losses list per optimizer so the figure can overlay all 4. Vanilla, SGD, theta, LRG. One line of update, we give it LR PUI3. Pushed any higher on this surface and the cliff axis diverges. So this is already near its safe ceiling. That ceiling is exactly why it's slow. The rate that keeps the steep axis stable is far too timid for the shallow axis. It logs its way to a final loss of 0.422. Momentum, carry a velocity v, decay it by beta 0.9, add the gradient, step along v, vu horn beta v, plus g, theta, LRV, same LROS2E3 as plain SGD. The only change is the remembered velocity. The cross canyon components in V cancel over consecutive steps. The down canyon component accumulates. Final loss 0.08. RMSProp. Keep S, a decayed average of squared gradients, and divide the step by S Curtis zips. S Dvoras betas plus 1 beta GG. Theta, LRG S Curtis 1 zips. With beta 09, EPS 1AI8, and a large LR 1A2, safe now because the per-axis normalization caps the effective step on the steep axis. Final loss 0.05. Adam, both states at once. M is the momentum estimate, S the RMSProp estimate. Both get bias corrected by 1, beta at exactly as last episode, then theta mol LRM hat squatties hat zips. LR1A02, beta 109, beta 2 is of 199. The bias fix matters most in the first 10 steps, when M and S are still warming up from 0. Final loss 0.03, the winner. 4 runners, 1 hill 0.42, 0.08, 0.05, 0.03. The headline isn't Adam wins, it's memory wins and Adam remembers the most. But notice we set every learning rate by hand, each near its own safe ceiling. Next episode we put that knob under the microscope on its own. The learning rate, too small and you crawl, too big and you explode, and the narrow band in between where everything actually works.